Hi guys, Kieran McAvoy here and welcome back to my channel. It's great to have you here. Today we're going to be continuing on with the Guide to Engineering Maths and we're going to be talking about the inverse matrix. What it is, what it does and how we can use it to solve simultaneous equations. So let's get into it. Alright, so far throughout the Guide to Engineering Maths we've mentioned the notion of an inverse multiple times. We've used it to actually find out how to compute the inverse of a 2 by 2 matrix. We've used the definition that when it's being multiplied with its counterpart, with whatever matrix it's the inverse of, when they're multiplied together it gives the identity matrix. And we're going to be talking about why that is today. Now, we've also mentioned it when we're using it in the Gauss-Jordan method of actually finding the inverse of a matrix. But we haven't actually really talked about what it is and what it's actually doing. Let's talk about how a matrix transforms space first. Let's recap that. So, if you've watched my other videos, you'll know that a matrix can take in a vector, so it can multiply a vector and output a new vector. So it maps a vector onto a new vector in the space, in whatever space it's working with. And when it does that, you can visualize it as transforming space. So it's morphing, it's stretching, it's scaling space. And what the inverse of that matrix then does, once it's transformed space, if we were to multiply that now, multiply all the vectors in that space now by the inverse, what that does then is it reverses what the original matrix has just done. Because it's just reversed it, if we were to multiply the two matrices together initially, say we had matrix M and we multiplied it by its inverse, then it essentially has done nothing to the two-dimensional space. I've also mentioned in my videos about the notion of understanding how looking at a matrix transformation, it tells us that the columns of that matrix tells us where the basis vectors I hat, j hat, and if you're in 3 dimensions, k hat, will go. So if we were to have a matrix that transforms the space and essentially does nothing, it outputs the same space, then what do you think the actual matrix is going to be? Well, it's going to be 1, 0, 0, 1, because the first column is going to be where the I hat vector is going to be landing, and that's just on itself again, and the second column is going to be where the j hat vector is going to be landing, so that's going to be on itself again. And you might notice this as the identity matrix. It is the identity matrix. And like I've said in the video on the 2 by 2 inverse, this is the notion that actually leads us to finding an inverse. The notion of if there's a matrix that I could multiply a certain matrix by so that it essentially cancels out its effect, it essentially does nothing, then I get the identity matrix. And we can then solve that to actually find out what this inverse matrix is. So the next thought is, do all matrices have an inverse? And the answer is actually no. Not all matrices have an inverse, and we call those matrices singular. Then the question is, how can we tell if a matrix is singular before we've gone to try and work out its inverse? If you have the two-dimensional plane and you're transforming the space, then all of those vectors, if they get collapsed down to a lower dimension, say it gets collapsed down to a line, so 1 dimension, there's no way of telling where those vectors were originally. So, in other words, there's no way to reverse the transformation. There's no way to actually get it back to where it was. Hence, there's no inverse matrix. We can tell that the matrix is singular and has no inverse by looking at its determinant. If the determinant is 0, as I've discussed in my other videos, we see that it collapses space down to a lower dimension. And if we're starting in whatever dimension and we collapse it down to a lower dimension, we no longer have that kind of space. So if we're starting in three-dimensional space and collapse it down to a plane or a line, two-dimensional or one-dimensional, then we no longer have volume, we no longer have this three-dimensional space. And the same goes for if we're starting in two-dimensional space and we're dealing with area and we collapse that down to a one-dimensional line, we no longer have any area, we no longer have that kind of space. And as we've just discussed, we can't reverse that transformation. So that tells us that the matrix does not have an inverse and is singular. So how can we use our understanding of the inverse matrix to solve simultaneous equations? Well, to do this we need to put the simultaneous equations into matrix form, and if you're not comfortable with that, then you can go and check out some of my other videos where I've explained how we actually get there, how we actually get it into the matrix form. We're essentially saying we have a vector v, let's say, and we're transforming that vector with this transformation matrix M, and that is being transformed or mapped onto the vector v dash. So we know where v is being mapped onto, which is v dash, and what we want to know is where v is. What we want to know is where it came from. Well, we can do this by reversing the transformation. We reverse the transformation from v dash back onto v. And how do we do this reverse transformation? Well, we use the inverse of the original transformation matrix M. In terms of the equation, we do this by pre-multiplying both sides by the inverse matrix of M. And on the left side, we're left with the identity matrix, because the inverse matrix of M multiplied with the matrix M will cancel out and give us the identity matrix. And on the right hand side, what we're left with is the matrix, the inverse matrix of M, transforming v dash back onto v. So that's about it, guys. Thanks very much for watching, and thanks very much for joining me. If you enjoyed the video, then be sure to leave it a like and subscribe to the channel if you're enjoying this kind of content. And you can go and follow me on Instagram and Facebook, because I post there daily on what I'm getting up to and what I'm thinking about doing for the next project, the next video, all the rest of it, some questions, all that good stuff. Thank you very much for watching. I will see you all in the next video. Bye bye.